top, section 2 of chapter 5, which introduces the idea that the electron configurations we've talked about so far are organized in such a manner that they have the S elements all together, the P elements all together, the D's all together, and the F's all together. We call them blocks. They're also going to have a logical organization in terms of periods. So remember we talked about that in section 1, is that whole periodicity idea, which says everything is arranged in terms of patterns. The length of every period is determined by how many electrons there are in those specific types of sublevels. So for instance, in an S orbital, we can only put 2 electrons. In P, we can put up to 6. In D, we can put up to 10. And in F, we can put up to 14. And the numbers that come in front of the S's also indicate the row of the period. Please remember that if you miss something on lecture, that it is posted on Canvas for you. So if something isn't filled in, or you miss a word, you miss a sentence, you can always go to Canvas to find it. So just like we can talk about them in terms of blocks, which we've seen before, we can also describe them in terms of groups and where those groups are located. Okay, we've seen this one before, where if we talk about elements in this particular set of columns, there's 2 groups here. All of those elements are what we call S block elements. Right? If our element lands over here somewhere, it's a P block element, and D and F just exactly how we've seen before. The first 2 groups are the S block. Group 1 has a special name known as the alkali metals. It includes those atoms you see. In their pure states, group 1 elements are incredibly reactive, silvery like they should be since they're metals, and soft enough that you can cut them with a knife. Group 1 elements are very reactive, meaning they will react with water in an explosive way, they'll react with air, etc., etc. Group 2 are the alkaline earth metals. They have a special name as well. They contain all of the metals that you see on the periodic table up in group 2. These are less reactive than the alkaline metals, but are still pretty reactive. Group 2 metals are not found in pure form. In other words, if I go looking for calcium in nature, I'm not going to find calcium by itself. I'm going to find it attached to something else. A lot of times when we say that they're too reactive to be found in nature by themselves, they're part of what we call salts. And we'll talk about what a salt is later on. They tend to react with nonmetals to form a substance, stable substance. On their own, they are unstable. From there, we want to talk about two elements that don't belong on the periodic table. They just don't belong anywhere. So what we do is we put them in a place where they fit the best. Okay. The first one is hydrogen. Hydrogen has the electron configuration of 1s1, but that's where the similarities between hydrogen and group 1 end. Hydrogen is not overreactive as far as water is concerned. Hydrogen can be found in nature on its own as the H2 gas molecule. Hydrogen is pretty important, right? It's the lightest of the elements, but it is not, it doesn't have properties in common with group 1. It is commonly placed in group 1 to remind you that it can be both a metal and a non-metal, because it can act as both of those things. The other exception is helium. We place it in the group 18 area, but its orbital designation says it should be right next to hydrogen in the far left group 2. However, we place helium over in group 18 with the noble gases because it is remarkably stable. So it acts more like a noble gas, but it has the configuration that would place it over by hydrogen on the left side of the periodic table. It should be in the S block because it ends in S2, but we place it over in the group 18 noble gases. Real quick, do you have a pass up?
No,
Where are you coming from?
get back.
Oh, okay. Good. So, first up is going to be a reminder of how orbitals are filled in our electron configurations. And you'll notice that as you go down, obviously there are more orbitals to be filled until you're at the bottom. From there, we go 5s40, 5p. These are all things you're familiar with, right? If you started in that specific row on the periodic table, the period number that you see on the left, then you should have those orbitals on the right as far as the order of you filling, right? This table is out of date. It says there are only 29 elements in row 7. In reality, there are 32. We have discovered all of the elements in the 7th row. Okay. So without looking at the periodic table, don't look. Without looking at the periodic table, tell me the group number, the period, so the row, and the block where we can find this specific element. Who wants to try for the group number? Go ahead.
It's in the second group.
Correct. Group 2. All right. What about the period?
6.
6th. And what block? The S block. Nice. All right, so another one. It says without looking, write the electron configuration for the group 1 element in the 3rd period. Start from 1s if you don't remember what the noble gas is that comes before. Don't look. I'm watching long. Don't look. So it should start with 1s, 2, then what? 2s2. Then 2p. Then what? 3s. 1. Okay, let's look. So for part A, the element's in the S, it's in the 6th period, and it has that designation NS2, so it's in group 2. For part B, it's a third period element with 1 electron if it's in group 1, so you should have written 1s2, 2s2, 2p6, 3s1, which is specifically sodium. Our goal is to be able to take information from an electron configuration to identify the location on the periodic table. We've already done this in the opposite way, where we've looked for an element and then identified its electron configuration. Now we're trying to go backwards to identify how its electron configuration gives us an idea of where it should be. Okay. Alright, next one is going to be the transition metals. So we're going to talk about the D block next. The D sublevel starts with the N of 3. Remember, N is the principal quantum number. Tells us energy level information. For these particular things, you're supposed to fill them by filling the S in the row first, and then filling the D in that particular row. We call these the transition metals or transition elements. They're all metals. And they have very typical metallic properties, meaning they're shiny, they're malleable, so they're easy to hammer into sheets or shapes. They're ductile, which means you can pull them into wires, which is probably pretty good since most of our wiring is made of copper. They're good heat conductors and electricity conductors, which is also pretty good because most of our wiring is made up of metals that need to conduct electricity, etc., etc. Now you'll notice that the D's always have that one level less than the S that they happen to be located in, right? So that's why 3D comes after 4S. Or 4D comes after 5S. Or 6D comes after 7. Yeah?
So is there one here?
No.
So
D starts at 3. You should not have a 1 or a 2D. Just like P starts at 2, you should not have a 1. P. That make sense?
Mhm.
Good question. So we know the rules for filling. We need to learn the exception. I know, sad. Unfortunately, all rules typically have exceptions, and we all know this. For the D block, the one exception may occur where instead of putting 2 electrons in the s orbital, we only put 1. Okay? So when we're trying to identify the element, given just the electron configuration, we would count the total number of electrons in the row. How do we count the total number of electrons in the row? Do you remember? We gotta add the superscripts. So we're gonna take the 5 plus 1, and we're gonna see that we have 6 electrons in this particular row. You'll also notice that they've written 5s after 4d. Is that right? No, 5s should always come before 4d. That's wrong a few times in here. Fair warning. Okay. So now let's look at how many total electrons we should have. How many? 6. So now we're going to look at the periodic table. I'm going to give you permission to do the thing it says not to do. So you're going to count 6 over from the left. And remember, you're in what row? 5. So you go to 5th row, which is where rubidium is, and count 6 over. What group are we in? Look for the number at the top. We're in group 6. Do you see that? Count 6 over and you're in group 6. We're in element MO. Right? Okay, this is one of our exceptions. Group 6 elements specifically will have that particular designation. They'll have 5s1, 4d5. Or they'll have 4s1, 3d5. Does that make sense? Instead of having 2 electrons in S, they'll have 1 in S, and then they'll have an extra electron in D. So all of them end like that. They all have like a 3d5, 4s1.
Oh, so you have to count
Count the total number of electrons to figure out where you're at. Absolutely. It is one of 2 exceptions in the D block. And we'll talk about the second here in a little bit. Cool thing about D block block elements is if you know how many electrons you're supposed to have, you know what group you're in. So if you know that there are a total of 7 electrons because you added the D's and the S's together and got 7, then you should be in group 7. All of the group 6 elements have this special configuration. After group 6 and before group 6, everything goes back to filling the S and then the D. Okay. Here's the next one. Is the P block. This is the far right of the periodic table. Groups 13 through 18. They're typically referred to as main group elements when they are grouped with the S block. So if you add S and P together, we call them main group elements. There's a few reasons for this, one of which is that when we say main group, we mean most commonly found in nature. So if you look at the far left S block and the far right P block, most of the first 3 rows, are things you've seen before or heard of before. The first 20 elements in the periodic table are the most abundant elements in nature. From there, it gets trickier. Right? Like we see less and less of the things that are on the periodic table. The first 20 elements are the most commonly found in nature. We can find them attached to things, we can find them by themselves, it really just depends on where they're located. The P block does not have a single way to be described. The P block contains all 3 types of elements on the periodic table. It contains metals, nonmetals, and metalloids. There are 6 metalloids on the periodic table. The 6 metalloids on the periodic table form a sort of ladder between the metals and nonmetals. The first metalloid, and I do want you to write it down, is going to be boron. After that, we draw a ladder on our periodic table to indicate the others, starting at silicon, down to germanium, Ge, over to arsenic, As, down to antimony, Sp, over to tellurium, Te, ending in polonium, Po. So again, we've got boron, then we start here, we go down, we go right, we go down, we go right, we go down. So, if you watch, you'll see the ladder, right? The ladder starts here, stops there. Everything to the left of that is a metal. Everything to the right of the ladder is a what? Non-metal. Okay? What do you remember about metalloids? What characteristics do they have? Do you remember? Go ahead.
Some of metals and some of non-metals.
Correct. They have some combination of the 2 different properties. They tend to be semiconductors versus nonmetals, which are non-conductors, and metals, which are good conductors. They tend to be solids at room temperature, like metals, but more brittle, like nonmetals. There's a lot of them. Within the P block, we can talk about 2 groups by name. The first is going to be the halogens. These are the most reactive of the nonmetals, group 17. These guys are accomplished reactors. In fact, most of the time when we are looking for these specific elements, they have already reacted with something. Super reactive members of the P block. Some general characteristics of metalloids, or semiconductors, is that they are somewhere between metals and non-metals in the P block. All of the metalloids are in the P block. The other thing to note about things in the P block, the metals tend to be harder than those in the S block. They tend to be less dense than the D block transition metals. Have you ever heard the term heavy metals? Not the bands. Heavy metals like lead that we find in some of our water supplies and things of that nature. They're called heavy metals because of how dense they are. Things in the P block tend to be less dense than the things in the D block, the transition metals. You have a question, Paul?
So they're more dense than the S block or less?
They are more dense than the S block, but less dense than the D block. Good question. Okay. It says without looking, but you can look. Will you ever not be able to look at my periodic table? It says write the outer electron configuration. What does that mean? So start at the noble gas. Outer electron configuration is the same idea as the noble gas configuration. For the group 14 element in the second period. So where's the second period? The group 14. So what group are we in? 14. That's the up and down, right? What's our element?
Carbon.
Starts with a C. That would be carbon. The name of the element. Is it a metal, a non-metal, or a metalloid? A non-metal. Thank you. Okay. Last thing is our F block elements. There are only two groups of them. The first row of the F block is the lanthanides. They have similar reactivity to group 2, alkaline earth metals. They're all solids at room temperature. Pretty much the most exciting thing. They're pretty rare. Any F block element's pretty rare. Some of them have to be produced. The second row of the F block, the actinides are of course all radioactive. That is not where the only radioactive substances are located, it's just where the most radioactive substances are located. The entire F block is radioactive. When we say radioactive, we mean harmful to human beings. So think like uranium, thorium, plutonium, things like that. Other severely radioactive elements tend to be found further down. So the further down in your groups you go, the more radioactive items become. In the noble gases, radon is radioactive. It's why you have radon detectors in your house. They're located near usually the water heater or your furnace. You also have radium. Radium is a pretty radioactive element. Anybody know anything about radium? In a historical context, anybody know what radium was used for during World War II? No. World War I, actually. It was used because it's glow in the dark. It was used to paint clock faces on watches for soldiers. And the women who painted the clock faces used to dip their paintbrushes in radium paint and then lick them and dip and paint. So of course,
They did.
we discovered 3 or 4 years later that radium was killing people. It wasn't pretty. Think ingesting a radioactive substance and having no idea. Of course, the entire American public was told that radium was perfectly safe, and other people were drinking like radium water. You can still find radium water on eBay.
Really?
Absolutely.
Will you die?
Huh?
If you drink it, will you die?
No, you have to expose yourself to a lot. So, in the same group as radium, they started to notice that women's bones were deteriorating. Why?
Because it attacks the bone.
So in the same group as radium, what other chemical is in there that involve your bones?
Radiation.
Look up. Starts with a C. You drink calcium to build strong bones, don't you? Radium takes the place of calcium in bone. So when they were ingesting paint, their jaws started to deteriorate. Radium would just take the place of calcium instead of calcium doing what it needed to do to strengthen the bones. So, when we say things in a group are related, we know this to be true. Right? We've seen it happen chemically. Okay, so let's do a problem. Okay. We're going to go through and we're going to look at 4 different elements in the periodic table. I want you to name the element, identify as metal, nonmetal, or metalloid, and then tell me if it has high or low reactivity. The ultimate goal of this section. Start with A. First things first. What's wrong with A? It's a weird one, right? Where is the S supposed to be? In the front. And you'll notice there's only 1 electron, right? Okay, so you're going to add, this is where the second set of exceptions is. You're going to add an electron to the number of d electrons you have and get how many? 1 plus 9 is 10. The F block is completely full, so can we skip it all together?
Yeah.
Absolutely. So what element do we have if we have 10 electrons and we're in row, what row are we in? 6. Remember the thing in front of S tells us what row. So count over. I see it. What do you think? It's a 2-letter designation. Anybody? Go ahead, Lucy.
HG.
No. You're too far over. 10 total electrons. Don't forget the S electrons. Start from the S. You're 1 row up. I'm gonna go down 1. You should be in the 6th row. So what should we have? P, T. That's where we should be. We're in the 6th row. 10 electrons over, skipping the F's. Puts us at PT, that's platinum. Metal, non-metal, or metalloid? Metal. High reactivity or low reactivity? Let's say low, just because we didn't talk really about reactivity of the metals in the D block, but for instance, they aren't as reactive as things in like the S block, right? Okay, let's do number C, or letter C. First, identify the element. What row are we in? 3. 3s2, 3p6 is what element? Ar, argon. Metal, non-metal, or metalloid? Non-metal. High or low reactivity? Low, it's a noble gas. Instead of saying low reactivity, what could you say? No reactivity. Remember we said noble gases are inert, non-reactive. They do not interact with anybody, not interested. Yes?
So let's say on the test you asked us like how like much it would be like reactive.
Mhm.
We put,
I would say like compared to group 2 in the periodic table, how reactive is this particular element? Or compared to group 17 in the periodic table, how reactive is this element? So let's do letter B and I'll ask you that question. Compared to group 18 on the periodic table, how reactive is letter B? More reactive or less reactive? Identify it first.
Less reactive.
What element are we in? 3p5 puts us at chlorine. Is chlorine more reactive or less reactive than the noble gas to its right? More reactive by definition.
How do you know?
Remember, noble gases are non-reactive.
Isn't that in the noble gas?
Well, chlorine is not. We said this is 3s2, 3p5, right?
Yeah.
Okay. Is this more reactive or less reactive than the noble gas? And we said by definition, the halogens are more reactive. They're the most reactive nonmetals in the P block.
Okay.
We also said these, are they more reactive or less reactive than group 2? These are more reactive than group 2. Okay. Other reactivity we talked about. Completely not reactive. Not very reactive at all. Okay. They'll do reactions, but you probably got to put energy in to get it happen. We said this guy was about as reactive as group 2, and these are all radioactive. So are they reactive? Yeah. Pretty radioactive, which means active. All right, let's do D. 6s2, 4f6. So 6s2, you with me so far? 4f6 puts us at so metal, non-metal, or metalloid?
Metal.
Metal. Reactive, low reactive. High reactive, low reactive.
Low reactive.
High reactivity.
What the
How
heck?
about here? Higher or lower than this one? Lower. Remember, as you move left to right, from here, we see reactivity goes down. So less reactive, more reactive. Most reactive, also most reactive. Okay. Everything on the periodic table gets compared to group 1 and group 17 when it comes to reactivity. When we say reactivity, what do we mean? Do you remember? Okay, how likely they are to combine with another element. What else could we be talking about? They could be talking about how radioactive they are, so are they giving off energy? We could be talking about whether or not they explode when they interact with something else as well. Okay. All right. These are the solutions. So if you go back through your notes, there are solutions to every single thing that we just did. Go back and fill them in if you feel the need. All right. The next section, section 3. Your note. These notes are for homework tonight. Is going to talk about what we call periodic trends. Okay. Based on the location and organization of the periodic table, we can now describe certain characteristics or descriptions of our different atoms. And the first one we can describe is what we call atomic radius. In order to describe how atoms on the periodic table behave as far as their atomic radii are concerned, the first thing we need to do is to define how to find an atomic radius. We have to measure the atomic radius before we can compare the atomic radius of one atom to another. So in order to find this atomic radius, what we do is we bind two identical atoms together. We covalently bond two atoms together. Let's say lithium bound to lithium. In theory, when we bind the two together, their electron clouds overlap. What we can do is we can measure the distance between the two nuclei. Again, they have to be identical. Okay? Once we know distance, we take 1/2 of it, and that gets us the atomic radius. Of the atom. So that's how we calculate what it is. Otherwise, if you could, let's theoretically discuss this. If you could zoom in on a lithium atom, okay, let's say you got it all the way under the microscope and you saw the individual parts, would you be able to see the electrons? Probably not. They're moving pretty fast, right? We talked about that. Electrons move really, really fast around the nucleus. We also said they kind of move in these weird, unpredictable patterns, and that they move so fast it's hard to spot them. Okay? Would we be able to define the boundary of an atom very easily if we moved all the way in? Probably not, right? The boundaries of atoms are very difficult to see or describe. So instead of trying to do that, we came up with a method that actually measures atomic radius for us. Okay, yes?
Like what would it be measured in? Because it's
Well, that's a good question. It's a special unit called angstroms with an A, because it's not in centimeters or meters, but an angstrom is like 10 to the negative 28th, I believe, of a meter. It's a very, very small unit. It's a special unit reserved for specifically atomic measurements. Okay. Now that we understand what an atomic radius is, we can talk about what happens on the periodic table to atomic radius. And we call these trends for a reason, because they're generic descriptions of what happens. The first trend, as we move left to right, is that we increase by 1 per atom the number of protons and electrons. Protons are very attracted to electrons, always. It's the only reason the atoms even contain what they contain. It's the only reason they stay in the configurations they stay in. As you add more electrons and more protons, the force of attraction between the two increases. Because of that increased attraction, atoms get smaller as you move left to right. As we move down a group, we generally just increase the amount of stuff that an atom has. Protons, electrons, etc., etc. As we move down a group, we increase the amount of protons and electrons something has. Because we're just increasing by huge numbers from one row to the next. Remember that in the difference between, say, rubidium and cesium in group 5 and group 6, there's a lot of atoms, or there's a lot of subatomic particles that get added, a lot of protons, a lot of electrons. So things get bigger as we move from top to bottom. Think about the difference at the top of the group that has hydrogen in it. Hydrogen has 1 electron and 1 proton. If you look down at, say, potassium, it has 19 protons and 19 electrons, as well as a whole bunch of neutrons in its center. As we move down, things get bigger. Call that a stuff argument. We're just adding more and more stuff. Think paper mache. The more you add, the bigger it gets. Again, as we move left to right, as we move top to bottom, atomic radius. We will talk about ionic radii tomorrow. That's the end of class. You have a few minutes left. Again, your homework for tonight is the notes over section 3 of chapter 5.